with the talk, a quaternion version of the Mathieu functions. Please, Mike, are you ready?
Okay, thank you very much. Can you hear me now?
Yes.
Okay. I'm so sorry about these technical problems. In my case, the computer audio isn't working and I'm talking to you through my cell phone, but we'll see if everything will work out all right. So today I'm going to talk about a quaternionic generalization of the Mathieu functions. But before starting, I'd like to thank the organizers and to congratulate once again Enrique Ramirez Arellano. This is joint work with Joao Moraes of the ITAM in Mexico. And as the title of the talk says, I'm going to talk about quaternionic analysis and Mathieu functions. So I have to explain a little bit about both of these concepts. I think more people are unfamiliar with Mathieu functions, so I'll start with that topic first. The Mathieu functions were produced in 1868 in a memoir by Émile Mathieu, who was studying the vibrations of an elliptical membrane. And I'll explain a little bit about how this came to pass. But Mathieu functions, as you can see, are very similar to the trigonometric functions. They have in common that they have the basic ones, which are called CE and SE, have period 2 pi. They're all different periods. Let me show a little bit better if I can. Excuse me one moment. Yes. So the Mathieu functions have a parameter called Q, which determines the second order differential equation which they satisfy. And as Q increases, they differ more and more from the trigonometric functions. And you see when Q is equal to 0, it's exactly a trig function. The functions CE are like the cosine. They're normalized by having derivative equal to 0 at the origin, and the SE functions have value equal to 0, like the sine functions at the origin. So these have been, so they're really not so complicated as one might imagine. And those are the small CE and small SE Mathieu functions. Let's see, where am I? Okay, I see what's going wrong now. Okay, so you can think of them as being cosine elliptic and sine elliptic, and it's just like a generalization of the cosine of n times eta or the sine of n times eta. But there, if you change a sign in this formula and you replace the cosine with the hyperbolic cosine, you get the alternative or the modified Mathieu functions. Once again, they're normalized either by having the derivative equal to 0 at the origin or the value of the function at the origin. They're denoted with a capital C and a capital S. And these are analogous to the hyperbolic cosine and the hyperbolic sine. They're a little different because, well, naturally they're not periodic anymore, and they oscillate terribly, and they get bigger and bigger and bigger as the parameter. As the functions, as the parameter Q in the formula tends to 0, they don't exactly tend to the hyperbolic sine and the hyperbolic cosine. I'll talk about the asymptotics of this a little bit later on. So we have the two kinds of Mathieu functions, the periodic ones and the non-periodic ones. Sometimes they're also called radial and angular. The angular is like the trigonometric functions, and the angular are like the hyperbolic trigonometric functions. Okay, so now these functions come from solving the Helmholtz equation in elliptic coordinates. So the Helmholtz equation is the Laplacian, which you all know, and I'll write down the formula later on, plus a positive constant times the function gives 0. And if we put this in elliptical coordinates, the Laplacian operator changes to an operator that I'm going to call script L, which looks something like the Laplacian in the Xi and eta elliptic coordinates, but another factor comes from the change of variables. And if we look for a solution which is a product of a function of Xi by a function of eta independently, then we find that phi and psi, these two functions of eta and Xi, satisfy the two different kinds of Mathieu equations that we have seen. So this is where the two Mathieu functions appear. Now, the Mathieu functions separately, from what I've seen, from all I've read about them, there's a difference from the ordinary trigonometric functions in that a student can go a long way with sines and cosines and never know about hyperbolic sines and hyperbolic cosines. You can do this, say, in electrical engineering, Fourier series, and so on, just using the trigonometric functions. But I've never seen any serious work which only uses this circular or trigonometric by themselves, or only uses the hyperbolic or the modified Mathieu functions by themselves. It's the functions of two variables which always seem to be of interest. So these functions of two variables, a capital C times a small c, or a capital S times a small s, which are most important. Now, the elliptical coordinates can be thought of as being defined in an infinite semi-band of height 2 pi, and they're set to concentric ellipses, or the vertical lines correspond to concentric ellipses. But if you take a fixed xy point and you find its value in the elliptical coordinates, if the eta variable increases by 2 pi, it's like going around this common interval from -1 to 1, of these confocal ellipses. So you see there are some natural boundary conditions which the solutions to the Mathieu equation should solve if they're going to represent something that came from a physical problem. So I'll define S for symmetric of a number Xi naught, the set of all functions defined in the rectangle from 0 to Xi naught times 0 to 2 pi, which first have to be periodic. B, they have to satisfy the continuity of displacement. That is, what I would call is saying that F is at Xi equal to 0, at the left side of this infinite band. Really, it's just a periodic even function. And that's because we have to have some value at the left side, where the interval from 0 to pi is identified with the zero interval from from pi to 2 pi, but approaching from opposite sides. And if a function is differentiable, well, the derivative of an even function is an odd function. So we have the continuity of gradient, the three properties that define this set of symmetric, which simply refers to functions that could have come from a function of x and y. So now some notation to confuse things a little bit more. The C's are the positive functions and the S's are the odd functions. So we write a plus sign and a minus sign in the superscript to indicate the solutions. The Mathieu functions are just phi and psi. And when we multiply them together to get the solutions of the Helmholtz equation, I'll call them zetas. So these are going to be the stars of the show, the Mathieu functions of two variables, you could call them. And by construction, they satisfy the Mathieu equation in elliptical coordinates, and we call them meta-harmonic functions. Okay, and these are used to solve actual physical problems. So you need to know that you can represent all solutions in terms of the Mathieu functions. So that the collection of functions phi n plus and minus is a complete subset of the continuous functions from 0 to 2 pi. And the hyperbolic or the alternative Mathieu functions is a complete subset in the L2 of the of a finite interval and a C interval, and this can transform into complete subsets in the ellipse. So that ends the presentation on Mathieu functions, and now I want to talk about quaternionic analysis. Many of us have told students in complex analysis that complex analysis is based on the Cauchy-Riemann operators, which are combinations of the derivative with respect to x and y. And a function is defined as holomorphic when one of these operators annihilates the function, and then the derivative of the function is the other operator. But the interesting thing about these operators is that the magic property of complex numbers, I squared is equal to -1, permits us to factor the Laplacian. I promised I would write down the formula. It permits us to factor this sum of two squares in a certain sense, which you couldn't factor over the real numbers. So this is the magic of the complex numbers, that we can relate harmonic functions to holomorphic functions. Clifford analysis is a wide-ranging generalization of complex analysis, where you introduce different units, E1, E2, E3, and so on, to find an appropriate Cauchy-Riemann operator. And depending on how you set up the things, well, then you get a different kind of analysis of this variable. There is a great difference between this multidimensional analysis and the several complex variables that was talked about in the previous conference, because here we managed to treat all of this as a single variable. So it has more of the spirit of functions of one variable than functions of several variables. A particular case of Clifford analysis is quaternionic analysis, from the quaternions to the quaternions. A quaternion is a combination of four real numbers with three imaginary units, I, j, and k. The squares are -1. They anti-commute. They have very nice properties. And the Cauchy-Riemann operator, or the Fwetter operator, has many, many names, and many symbols are used for these kinds of things. Some people multiply by 1/2. This operator also factors the Laplacian operator. So I'm going to be talking about a kind of quaternionic analysis today. But all of these hypercomplex analysis involve producing results analogous to Cauchy's theorem, Cauchy's integral formula, series representation, the Borel-Pompeiu formula, and so on and so forth. A sort of a holy grail of this would be to try to get some kind of a theory that would then give results for ordinary several complex variables, but that still seems to be very far off. However, many results are accessible. We would say that a function is monogenic or hyperholomorphic or regular or sometimes just holomorphic when the Cauchy-Riemann or Fwetter operator applied to f is 0. Monogenic functions are always harmonic, so they're always real analytic. And let me show you a trick for creating monogenic functions. Start with a harmonic function u and just apply the conjugate operator d bar. This function f equal to d bar u. If we apply d to f, we get d bar u, which is the Laplacian applied to u, so it's 0. So f is automatically a monogenic function. So this trick comes up in many contexts. So that's basically what quaternionic analysis is. Special cases, there can be many combinations of dimensions. If one takes complex numbers as the domain, R2 to R4, then we have 4 functions of 2 variables each. This can be interpreted as a quaternion. And in this article by Luna, Perez de la Rosa, Rodriguez, and Shapiro, this analysis was studied, particularly in the case of the operator D plus lambda. And in this context, for this operator, the whole basic theory was worked out, the Cauchy integral formula, the Borel-Pompeo formula, and so on and so forth. All the basic work was done. And at the end of the article, it was mentioned that if you start with Mathieu functions and you apply D minus lambda, you get solutions of D plus lambda of the function is equal to 0. So I want to talk about that, but I want to change the context a little bit more. And for the rest of the talk, I will be talking about functions that take their values in R3 instead of R4. I'd call them reduced quaternionic functions, or that take values in reduced quaternions, which is where the last component is equal to 0. So now we have functions of 2 variables, and there are 3 functions. The operator, which was considered by Luna et al. In the article I mentioned in the previous slide, is I times the derivative with respect to x plus j times the derivative with respect to y. If we add lambda, we get a so-called Moisel-Theodorescu operator, lambda plus d, lambda plus the scalar part is the lambda, and the vector part has an I and a j. In this case, d minus lambda is simply minus the conjugate of this operator. The conjugate of d is minus d. The square of d is minus the Laplacian. So we get the factorization that d plus lambda times d minus lambda is minus the Helmholtz operator. This was observed many years ago by different authors. So we can apply the trick that I just mentioned. If you take any solution of the Helmholtz operator, in other words, zeta is a lambda meta-harmonic function, a scalar valued function, we apply d minus lambda to the f, giving an R3 valued function, then d plus lambda of f is 0, and we say that f is lambda metamonogenic, taking values in reduced quaternions. Okay, just to notice something that somebody might not realize, when you multiply this reduced quaternionic operator, it only has scalars I and j, by a function, R3 valued, only scalars I and j, a k term appears. So this was what Hamilton discovered a couple of centuries ago, that you cannot make a nice multiplication that will stay in R3. So the d plus f equal to 0 is a system of 4 differential equations. An interesting fact to note is that if this derivative is 0, the f naught, then the f1 is 0, because I'm always assuming lambda is different from 0. So if f is lambda metamonic with lambda different from 0, and the scalar part of f is constant, then f1 and f2 are 0, so f is identically 0. We'll come back to that before, but I haven't found in the literature that anybody has ever noticed this fact before, but it's quite elementary. So we have functions in the plane or in the ellipse, and in functions in the elliptic coordinate. The L operator that corresponds to the Laplacian I've already mentioned, corresponding to the D operator, we have this expression in elliptical coordinates, and the factorization exists on both sides, d plus lambda, or the script d plus lambda. And when I say that a function is metaharmonic, technically it should be a function of x and y, but I might use the same word for a function in elliptic coordinates, and the same for lambda metamonogenic. So we have these spaces of functions, the lambda metamonogenic functions, the L2 lambda metamonogenic functions, and the same things in elliptical coordinates in a given rectangle. In the rectangle, we use a weighted inner product, which corresponds exactly to the unweighted inner product of the corresponding functions in Cartesian coordinates. So now I can begin the subject of the talk. We fix a value of lambda in the reals and different from 0. We define the lambda reduced Quaternion Mathieu functions, which is simply we take the Mathieu functions, which you will recall are a phi of, I forget which one, phi of eta or psi of phi. Phi of, well, anyhow, it's the product of the two Mathieu functions. We and therefore meta-harmonic. We apply the conjugate operator and divide by minus 1 over lambda for technical reasons. So essentially, we're taking the Q Mathieu function with Q equal to lambda squared over 4. And by the trick I just mentioned, this Mathieu function called M of n, depending on lambda, is automatically lambda metamonogenic. Its scalar part, well, the scalar part comes by taking away the d applied to a scalar function is vectorial. So that's not the scalar part. The lambda part is real. Lambda is real. So we get the scalar part of the scalar function, and minus 1 over lambda times minus lambda is 1. So the scalar part is just the same zeta function that we put in the ingredients for constructing this function. So basically what this operator does is takes a scalar function and produces an R3 valued metamonogenic function. Okay, so if you write it out all in coordinates, we have, as I promised, the scalar part is the zeta n. And the I and j parts can be expressed in terms of hyperbolic sines, ordinary sines, hyperbolic cosines, ordinary cosines, and the Mathieu functions and their derivatives. We put these all together and we get the Quaternionic Mathieu functions of the title of this talk. The scalar part is as prescribed, and these, if you limit to a finite rectangle, these are always square integrable lambda metamonogenic functions. Okay, so here's an example of a scalar I and j part in elliptical coordinates and in the original ellipse when you change the coordinates back. Okay, so some results. If you fix lambda, the three-dimensional functions, m, n, plus, minus, form a complete system in the lambda metamonogenic functions in the coordinate rectangle or in the ellipse, whichever way you want to look at it, in the sense of uniform convergence on compact subsets, and also a complete system in the corresponding Hilbert space with the weighted inner product. Okay, so to prove this, just to have an idea, you take a function, perhaps square integrable or perhaps not, depending on which part of the function you're proving, which part of the statement you're proving. And we have the completeness results that I mentioned before for real valued functions. We can approximate the scalar part f naught by the real valued classical two variable Mathieu solutions, the corresponding metamonogenic functions. And now we need to fill in the I and j parts. One way is to write down the series and use those same coefficients for the I and the j parts, but it's very hard to see that that converges. So instead of that, we apply this completion operator or harmonic conjugate operator or whatever to form a function g, and g and f have the same scalar part. And so g minus f is a lambda monogenic function whose scalar part vanishes. And by the interesting fact I mentioned at the beginning of this discussion of the operator d, we have that g equals f. So to get this to work, when you work out the details, you need to check first that the uniform limit of lambda metamonogenic functions is lambda metamonogenic. So that's another story. And then to prove the result for the Hilbert space M2, you have to do a result analogous of what's done in Bergman space theory, which says basically that the projection, the evaluation operator of a holomorphic function is the continuous operator, which implies that the corresponding space of holomorphic functions or whatever you're looking at is closed in L2. So with those results, you can prove these completeness theorems. Okay, now the elliptic coordinates, the vertical lines in the coordinate rectangle correspond to this family of confocal ellipses who have the foci at -1, 0 and 1, 0. And as the parameter C naught that corresponds to the position of the vertical line, the right side of the rectangle, tends to infinity, these ellipses get bigger and bigger, and they get more and more circular. So the eccentricity is actually equal to 1 over the cosine of C naught, but it happens that the right side of a given ellipse is the hyperbolic cosine of C naught, and the height is the hyperbolic sine. So if we multiply by the eccentricity, all of these ellipses are rescaled to the unit disk. So that's sort of a more natural domain to work in some sense. We have mu times the C value that corresponds to mu by inverting the operation described here. So this has been well studied, but it turns out in the literature, like in this very detailed book by McLaughlin in 1951, the asymptotics that I talked about at the beginning, the asymptotics of the Mathieu functions are worked out in great detail, but there are some very confusing things. It says that the cosine and sine elliptic, or the Mathieu functions, tend to some multiples of the Bessel functions. But actually, this is not true. The coefficients Pm prime and Sm prime are functions of Q, and both sides of this relation tend to infinity. And really what happens is that the left side is asymptotic to the right side when there are certain relations among these quantities. And this notation of the arrow, which really means asymptotic to, confusing as it is, appears in many articles from the 30s, 40s, and 50s. So really what's happening is the following. If we take the unit disk, complex number W, or XY, UV and W in the unit disk, we fix an eccentricity and we go backwards, dividing by the eccentricity to get the big ellipse. Then we can go backwards in elliptic coordinates, although the formula is almost impossible to write down. And going back to the picture, what we have is that if you pick a point W, when we make the eccentricity small enough, W will be inside the corresponding ellipse. So suppose we have a family, one parameter family of Q values tending to 0, such that Q of mu over mu has a limit. 2 times this we'll call the limit alpha. Then, as I said before, the phi first, the CE function, the cosine function, the Mathieu function tends to the cosine. So this notation is that the capital phi is cosine and sine, and the modified or the hyperbolic ones tend to are asymptotic to with exactly a factor of Q of n over 2, which is what was hard to understand in the literature, to a multiple of the beta function, taking into account the limiting value of the ratio between the square root of Q and the mu. So this is basically what McLaughlin and others were saying. And using that, if we take the Quaternionic Mathieu functions, if we use the appropriate lambdas and we multiply by the appropriate powers of u, we get a collection of functions of different lambdas, but they have a limit, which the scalar part as a limit is well known in the literature, and the I and the J parts are rather different. And it seems to be that there are a new collection of functions here, which are alpha metamonogenic in the unit disk. Okay, so here is a graph of just the scalar part for a rather eccentric ellipse. We have a certain value of these functions. The scalar part, you see it gets bigger and then gets smaller, and as q is nearly 0, we see how they approach the actual limit. The third graph was calculated by a completely different formula than the three at the left. The three at the left are the Mathieu type functions, and the one at the right using the Bessel functions. Now, for some problems, one is interested in like a vibrating membrane, Mathieu functions which are 0 on the boundary of the ellipse. So this graph is a little confusing. I'm going to fix an eccentricity mu and then take the corresponding value of c and see what happens when everything is a function of q. It can be proved that as q goes to infinity, these functions are oscillating, so they have an infinite number of zeros. They're all simple zeros. So we'll call q nm the mth positive 0 of this graph. So we have the psi plus and the psi minus graphed here in blue and tan respectively, and we have the different first zeros, the different second zeros, the different third zeros, and so forth. And the asymptotic value of this is precisely the mth 0 of the nth Bessel function of the first kind. So this is very well known, and we can apply this asymptotic behavior to create what are classically known. This is found in studies of the movement of an elliptical lake, for example, and other problems, some electronic problems. These are real value functions where we use these zeros of this function of q as the parameter in the Mathieu functions of two variables. So be careful when I talk about a zeta with two subindices, I'm talking about a particular value of q and m. And since this value is 0, automatically we have that at the right side of the coordinate rectangle, the zeta n m plus minus take the value 0. So these are can be called zero boundary Mathieu functions. They're useful for certain kinds of physical problems. And an interesting article by Goldstein in 1927 proves that these form a complete orthogonal system in, you can approximate any continuous function which is 0 on the right boundary in the sense of L2 with this system. Note that these zeta m and m's are meta-harmonic, but for different values of q. So when you add them together, you get a mess. It's like the sines and cosines of n theta, which are solutions of different second-order differential equations. They're all different equations, but together they form a complete system in the theory of Fourier series. So if we take this complete system and we apply, we simply consider the R3 valued functions, the Mathieu functions, with the corresponding parameter that has to be 2 times the lambda is 2 times the square root of q. We introduce the zero boundary reduced Quaternionic Mathieu functions. Now these functions automatically satisfy that the scalar part vanishes on the boundary for all values of eta. So if you don't believe me, maybe I can help you with a picture. These are some graphs with different values of n and m. And as you can see, the scalar part vanishes very nicely on the right edge of all of these rectangles, whereas the I and the J components have no need to vanish. But so that the name zero boundary RQM functions is a bit of a misnomer. It really means only that the scalar part vanishes at the boundary. So one result is that these things form a complete system in, this should say the ones that vanish on the boundary, the closure of the compact support. This is mistyped, but that they're orthogonal. I'm sorry, they're all orthogonal in R2. You see, when you write out each of these in coordinates and you look at what the scalar product means, by the previous theory for scalar values, the integrals of the products of the scalar parts will be 0. But when you put together the other parts, you get quite a long and interesting calculation that I won't go into. The second fact is that they are they're complete in the symmetrically, or the functions that this should say F that are in the S naught of psi that I defined before, that satisfy the 3 symmetry conditions A, B, and C, and that they extend continuously to the right boundary edge, because ordinarily we have the open right rectangle, and that any function which is in this space can be approximated in the L2 sense with this weighted scalar product by these so-called zero boundary functions. So the scalar part is approximated very nicely, but to check that the other parts work is rather complicated. The proof is rather a beautiful experience. You see, the inner product of a function f with one of these purported basic functions can be written out explicitly. And then you integrate by parts. When you integrate by parts, you have to use every property that you have at hand, that the f naught, f1, and f2 are 2 pi periodic, that they're even functions on the left boundary. All of these things come in, the odd function on the derivative on the left boundary. And when you finally use all of these properties in a beautiful way, you get that if f is orthogonal to all of these basic elements, then 0 is equal to this integral, the sum of 2 integrals on the right-hand side. But if you look here, we have the quadratic Laplacian, the elliptic coordinate Laplacian of f, and here we have the f naught. And putting them together, everything comes out in an exact way that 2 times the square root of qnm plus lambda times the integral of f naught using this weight function. And there's some steps that I've left out in the derivation, times the classical zetas is equal to 0. In all probability, lambda will be different from all of the minus 2 squared of qnm. And so if we are lucky enough for that to happen, this integral is always 0. And by the completeness theorem for the zetas, we get that the f naught is equal to 0. However, it could happen that lambda is equal to 1 or more of these qnm's. By the increasing property of the q's, it would be only 1 m for every n. And so if lambda is equal to some of these, basically what this says is that lambda has to be in the linear space generated by the corresponding zetas. And so it's not hard to argue that lambda is lambda monogenic in that case too. So in all of cases, probability or no, we finally proved that if lambda is, if f is orthogonal to all of the zetas, then f naught is equal to 0, and then the rest of the f1 and f2 follow suit. So that's how to prove the completeness. So now I want to go into the last topic, which is what we call the imaginary time wave equation, an application of the above theory. The wave equation is what you get when you take the Laplacian and you subtract a positive constant times the time derivative. So if you apply the transformation to imaginary time, you get this imaginary time wave equation. These kinds of things appear in quantum mechanics. And if we look at the same equation instead of in an ellipse, we look in the coordinate rectangle for elliptic coordinates. We have the elliptical version of the Laplacian operator. K squared times the derivative of time doesn't change because we only apply the elliptical coordinates to the spatial coordinate. So this is the equation I want to discuss a little bit. Let's assume a real valued, scalar valued initial condition underscore v, function of elliptic coordinates c and eta. We assume it satisfies all of the symmetry conditions that it came from an actual physical problem, and it also vanishes on the right-hand boundary. So let's assume it extends continuously to the boundary automatically in L2. Then by the classical results, the result of Goldstein, which I cited a moment ago, we can represent it as an expression in the complete system of the classical Mathieu functions with the Q values chosen so that they vanish on the right-hand boundary. So we have some coefficients A and M, which give us this initial condition V. Now I want to introduce some constants, omega and M, analogous to frequencies, which are the 2 squared of nm divided by the parameter k appearing in the wave equation. And then with this, I can construct a solution to the equation. So the result is if we use the same coefficients that were previously applied to the zetas, which were scalar valued, and now we apply them to the R3 valued reduced quaternionic Mathieu functions for a particular mu naught that has been behind everything, and multiply it by exponentials with coefficients of these omega and m that were conveniently defined. This we can call the imaginary time quaternionic value wave function. This is a reduced quaternionic solution of the imaginary time wave equation. Not only that, it's the only real analytic solution whose scalar part at time 0 is precisely the boundary values that we prescribed, and its time derivative is what you get when you take the time derivative of this at time 0. And not only that, it's a solution of the time-dependent R3 valued Mosul-Teodorescu equation, taking the D operator plus K times the first derivative with respect to time applied to V is equal to 0. Okay, so to prove this, well, first, if you apply D plus K partial with respect to time, that's the last step here, to one of the terms in the series, the zeta nm times the e to the omega nm times time. Well, the D only applies to the spatial coordinate. So we get D applied to the spatial coordinate, and the time is just a factor that, like a constant factor. And the partial derivative with respect to time only applies to the exponential, so a factor of omega nm comes out into the formula. But we know that the ZNMs by construction are 2 squared of QNM metamonogenic. So this is equal to 0. So we have different metamonogenicity. Every term we use a different metamonogenicity. We multiply this thing by A and M plus minus. So we multiply these numbers here by A and M plus minus, and we get V. So D plus K partial with respect to T of V is equal to 0. If we apply D minus KD with respect to time, we get the operator of the imaginary time wave equation, L plus k squared second derivative with respect to time. So automatically we have that this is a solution of the differential equation. It's very easy to check that it satisfies the initial conditions almost immediately from the construction, and to see that it's unique, if we have another condition which satisfies the same boundary conditions and the differential equation, well, this difference W, its scalar part vanishes at time 0, and also the time derivative by the conditions we've imposed. And since this operator applied to W is equal to 0, and this operator is a real valued operation, the scalar part also satisfies this second order partial differential equation. And now we can apply the Cauchy-Kovalevskaya theorem to get that W naught is 0 for all positive time and all points in the space. So, so now we have that the D, the script D, since we're working in elliptic coordinates, dW plus K times the time derivative of W is 0. So I put the D on the left side and the K on the right side. Now, the partial derivative of W with respect to time, if W naught is 0, this is only a combination of I and J. It has no scalar part. So it's in the scalar part of the R3 space. When you apply the D operator, which only has I and J, to W, which also only has I and J, you only get scalars and K. If these are equal, we have an I and a K thing equal to a J and an R thing. These are complementary subspaces. So now we know that dW is 0 and the time derivative is 0. From this, we get that W naught is always 0. And so W is always 0 because of the connection of the W naught with for metamonogenic functions. So that proves this application. Now, what does this mean? These coefficients omega are positive. Unfortunately, they're not imaginary, so it's not periodic. This equation, if you try to interpret it in real time, it would be, for example, an elliptical membrane of negative tension. That is, that when you when it's stretched, instead of stretching back, it tries to stretch more. So let's take a particular boundary value. So this boundary value I just created by randomly summing for n equal to 0 and n equal to 1 with some convenient conditions. But I also included some terms with m equal to 15 and a coefficient of 1/10,000th. So you can't see them in this graph. However, if I can find the picture, one moment. You can, well, I got it in the middle of the time evolution. So in a moment, it will go back to the beginning. Okay, now you can see the time, this is the initial value at the left. It's growing exponentially, but the other terms, which are very small, are growing faster exponentially, and they leave the original part that was visible behind. So this is what the numerical application of this type of partial differential equation follows. Everything that I said could have been done just as easily with complex quaternions. And with complex quaternions, we can factor the standard wave equation and develop a similar theory that quaternionic Mathieu functions will be different in that case, of course, and they will solve this corresponding problem. So that's all that I have to say. Thank you very much.
Thank you very much, Mike. Yes, for this interesting talk. Some questions, remarks, comments, please.
Yes, I will have a question. Professor Mike, if you begin with this operator D, the calligraphic D, as a factorization of the Laplace operator. Have you considered working with arbitrary factorizations of the Laplace operator? Or, well, or maybe just a perturbation of this operator D in such a way that it is still being a factorization of the Laplace operator, and then to see how everything evolves?
No, what kind of factorizations would you use?
For example, some time ago I was trying considering them that, for example, the Laplace operator, you can see that as the, how do you call it, out, is the trace of a matrix which has all the derivations on the main diagonal. And then if you factorize this matrix as the multiplication of two matrices, two different matrices, you could obtain also factorization. And many operations seems to work very well for any kind of operator. But this is something that, well, it's something wild idea that I have some time ago.
Yes, these ideas can be taken in many, many directions. Yeah. Another direction is to use different coordinates other than Mathieu functions for different kinds of domains. Another thing is to do the same thing. Well, we're working on this in full quaternions, but some other things happen. Okay. Clifford algebras. There are many, many directions which these ideas can go. There's plenty of room for people to look at. If we had a convenient square root of the time operator, then we could factor more operators and okay. so on and so forth.
Well, you have one, but it's a very large one. You need to know the time in the future. But well, thank you.
Thank you. Okay.
Thank you.
More questions? Comments? Okay. If that's the case, we continue in 7 minutes with the talk of Professor Nikolai Vasilyevsky. Thank you very much.